Good morning and welcome to our next installment in trigonometry. We're going to be looking at inverse trig functions, which are those three buttons on your calculator that you'll see above sine, cosine, and tangent, and they're used to undo sine, cosine, and tangent and give you angles. So you can think of them as like the square root button to the squared button, or the natural log button to the e to the x button. These are inverse functions for each other. And so in order to understand these inverse trig functions, we're going to have to take a look at the graphs and figure out when they're going to be one-to-one. You know, like you can't, for example, x squared, the parabola, you can't take the whole parabola for the square root because it's not one-to-one if you have the whole parabola. You only choose the positive half of the parabola for the square root function, and so forth. So we're going to see the domain and range of these functions appear from the graphs. We're going to look at the graphs to find the domains and ranges. Okay, so here are our learning objectives. We're going to define these three functions: inverse sine, inverse cosine, inverse tangent. And in particular, we're going to define their domains and ranges. And then we're going to use the inverse function to solve some problems. Okay, so let's go ahead and dive in. So inverse cosine, we'll start off with cosine first. That's been our kind of standard progression. It's been cosine, sine, and then tangent, x, y, and then y over x, or slope. So for cosine, we're going to say the inverse of cosine is inverse cosine of x, our input, equals y. Well, what is y, you ask? Y is the number between 0 and pi, so that's what this part means. This part right here means number between 0 and pi, between 0 and pi, inclusive, so it could be 0 and it could be pi, where the cosine of that number equals x. Okay, so it's defined in terms of cosine. So we really have to understand cosine to understand the inverse to cosine. Just like you need to know x squared to understand square root of x. Okay, so it is the cosine inverse of x is the angle between 0 and pi, where you take the cosine and you get whatever you put inside the inverse function, x. Okay, so that's this. Another way of saying this is cos inverse of x is the angle between 0 and pi, inclusive, where the cosine is x. And you might ask, why do we have this restriction on y? Why is it that y can only be numbers between 0 and pi? Why can't we allow y to be any number? And it comes down to the graph of the function and when it's invertible. When is it one-to-one? So it's not one-to-one without this restriction from 0 to pi. And this is, in fact, the biggest domain we could take for cosine that's near 0. Now, we could actually take from negative pi to 0, but when you have a choice between a negative domain and a positive domain, the convention is to take the positive domain, just like square root and x squared. When you're doing x squared, and you want to make it one-to-one, you take the positive half, all the numbers, here I'll just draw it for you. When you're doing x squared and you want one-to-one function, then you just take the positive half. So you would take the numbers that are to the right of 0, so those guys. And then it's one-to-one, okay? You could take the left half, but that's not the convention. So let's go ahead and look at this graph of cosine, and from the graph see why we need this restriction. Okay, no, wait, bottom right corner. So here is the, first I'll just graph cosine of x. There's cosine in all its glory, and you can see the radians on the x-axis. Those are our angles. So if we look at the graph of cosine, you can see that it fails miserably the horizontal line test. So if we were to say y equals 0.5, for example, I'm going to use a different color. So if we look at this line y equals 0.5, or we just say like y equals a, oops, I don't want a, b, let me make a slider, c, So here's my slider, and I want it to go between 1 and... Okay, so you can see any horizontal line we choose that hits the graph, hits it in an infinite number of places. You know, you zoom out and it's going to keep hitting that graph of cosine no matter how far out to the left or to the right you go. And so this is a really not one-to-one function, right? We have this infinite set of answers for where the cosine is 0.36. You know, it's like right here and there and so forth, and you just keep adding periods and you go on forever. So in order to get a single answer out of this, we have to take a very small snapshot of the function. We have to take a small piece that is one-to-one. And so we'll start around 0, and you might say, well, okay, what if I go to the left and to the right? So if I go to the left and to the right of 0, then we're still not one-to-one, right? Because we have this little piece of graph, and it's symmetric on either side of 0, and so we'd end up getting 2 answers out if we tried to make our cosine inverse function go right around 0 to the left and to the right. So we end up going to the right, and we take this part, and it's still one-to-one if we go to the right all the way down to and including pi. The moment we turn the corner back, we'd have a little piece of graph that is no longer one-to-one, okay? So it would match up with these y values over here. So we want this, oh, you can't see the blue, here, there we go. So we want this chunk of the cosine graph. We want the cosine from 0 to pi. And you can see from this picture that is in fact one-to-one. This is just a part of the cosine's graph, and there's no double hitting when we look at these intersections, right? All these horizontal lines only hit the graph once, okay? And that's the key to it being one-to-one, is that every horizontal line intersects the graph in at most one place, okay? So that's our domain for cosine, so that it's one-to-one. 0 to pi, inclusive. They should really be or equal to. Okay, so that's kind of the reasoning for this. That's the reason for why our answers, so the cosine inverse function, the answers are going to be numbers from 0 to pi. They're going to be angles in that set of numbers. Okay, let's look at the inverse sine. So the definition of inverse sine is a similar kind of definition. It's defined in terms of sine of x, or sine, actually sine of y. So we'd say sine inverse of x is equal to y, where y is the number between negative pi over 2 and pi over 2, such that the sine of y is x, okay? So another way of saying this again is sine inverse of x is the angle between negative pi over 2 and pi over 2. So the smallest answer is negative pi over 2, and the biggest answer is pi over 2, where the sine of that angle is x, okay? So you take the sine of the angle and the sine of whatever is inside of there, So if you wanted to find out what the answer to sine inverse of 0.5 is, that is the angle where the sine of that angle is 0.5. Sine inverse of 0.7 is the angle where sine of that angle is 0.7, so forth. Okay, so let's look at the graph. And again, see why we have this restriction between negative pi over 2 and pi over 2. So there's the graph of sine of x. And if we look at sine, we can see that, we'll go zoom down into the corner again. Okay. Oh well. So if we look at the graph of sine of x, we can see again it's not one-to-one, just like cosine. So starting at 0, we can start to look, we want to take as much as much of this graph as possible where it passes the horizontal line test, so where it's 1 to 1. And we can look, starting at 0, we can go in both directions, and it's still 1 to 1. So it's, you know, we're going to go to the right from 0 and to the left from 0. So we'll go in both directions and maintain that 1 to 1-ness. As soon as we curve and turn the corner right here, our graph is no longer 1 to 1. So right here, if we were to take a little piece to the right of pi over 2, we would fail the horizontal line test right around y equals 1, right? Let's get that line y equals c going again, and set c equal to -1. I want c to go from -1 to 1. Okay, and let's make this a little different color. Perfect. Okay, so you can see right here, oops, I want this to be 1 up here. You can see when our line y equals close to 1, if we were to take a little bit of the graph to the right of pi over 2 and a little graph to the left of pi over 2, we would hit it twice, and we don't want that. It's not 1 to 1 if it hits the graph twice or more. So that means we need to stop right at pi over 2 as we move to the right, and then as we move to the left, we have to stop right at negative pi over 2. So that's going to be our domain for the inverse for sine of x, so that it's 1 to 1. That's the chunk of sine that we want that's invertible, okay? So we can see now, if we just go between negative pi over 2 and pi over 2, that the sine of x is 1 to 1 the whole way. That this line only hits it exactly once, which is really nice. And that's the key in order to come up with an inverse function. So that would be the range, our set of answers for the inverse function, our numbers from negative pi over 2 to pi over 2. The next lesson after this one, we'll take a look at the graphs of these functions, and then also kind of like how we can use these to come up with the sets of all the answers to cosine and sine problems. Okay, and lastly, inverse tangent. So inverse tangent of x is again y, where the y is the angle from negative pi over 2 to pi over 2, not including, and we'll see why it's not including those numbers, where the tangent of y is equal to x. Again, it's defined in terms of what the tangent is. Tan inverse of x is the angle, where tangent of that angle is whatever x is, whatever you put in. So when we look at the graph of tangent, we can again see why we have this restriction on the answers to inverse tangent. So in order to make this 1 to 1, we need just one of these chunks of graph, right? One of these nice kind of cubic looking curves. They're not exactly cubics because cubics go off to the right and to the left forever. And in these, they have these asymptotes where they blow up to infinity. So we'll take the chunk that's right around 0, and what's really nice is that this entire graph is increasing from negative pi over 2, or close to negative pi over 2, all the way to pi over 2. The whole function is increasing as you move from left to right. And so that makes, that's quite nice because an increasing function's 1 to 1. We can see that every time you move right, your y value increases. And since it's increasing the whole way, the slope is increasing as the angle increases from negative pi over 2 to pi over 2, then this is 1 to 1 for this entire chunk of function. So in this case, we would go from negative pi over 2, not including, because that's actually not a possible angle to put into tangent, you would get undefined, all the way to pi over 2, not including, because again, that's not a possible angle you could plug into tangent, so you couldn't get it out of the inverse function. And so this is the graph of the invertible part of tangent. Excuse me. This is the graph of the invertible part of tangent. So you can see that our set of inputs go from negative pi over 2 to pi over 2, and the outputs go through all real numbers. Right? So it goes all the way down to negative infinity and all the way up to positive infinity. Okay. So, all right, those are our definitions for these inverse functions. What the graphs you saw were not the graphs of the inverse functions. I want to be very clear. The graphs that we were looking at were the graphs of cosine, sine, and tangent, restricted down to make them one-to-one. So the graphs we were just looking at were restrictions on our cosine, sine, and tangent graphs so that they would be one-to-one. We'll look at the graphs of the inverse functions a little bit later. Remember that you can always get the graph of an inverse by reflecting the graph of your function across the line y equals x. So if you reflect it across the line y equals x, you get the graph of the inverse function. But we're not going to do that in this lesson. We'll do that in the next lesson. Okay? So let's go ahead and look at the domains and ranges of these functions. Hopefully you already have a sense of what the domains and ranges are because we were looking at the original function in its one-to-one state. So we were looking at the one-to-one part of the original function, and to get the domain and range of the inverse, you just swap domains and ranges. Okay? So let's look at the domain and range first of the original functions. So cosine of x's domain is all real numbers. You can plug any angle in, and the range is -1 to 1. Now, what we found was that the cosine, that the domain that was 1 to 1 was actually, we took the, I'm going to put another column over here, 1 to 1 domain, was actually from 0 to pi. So that was the domain we took for cosine so that it passed that horizontal line test. Sine of x's domain was from -pi/2 to pi/2. And so the sine's domain in practice is all real numbers, but in order to have it be 1 to 1, we have to go down to that smaller domain of -pi/2 to pi/2. Its range is also -1 to 1, so we'll see that show up in the inverse functions domain. Tangent's domain would be all real numbers except for pi/2 plus multiples of pi. Those are all those angles where the cosine is 0. Its range is all real numbers. The 1 to 1 part of tangent was this chunk. It was the chunk from -pi/2 to pi/2. Okay, that was the chunk of 1 to 1 domain for tangent. Okay, and it didn't include -pi/2 and pi/2, unlike sine, because you could not actually plug those numbers in to tangent. Those are undefined tangents. So now we just take a look at the range and domains, or domain and range for those three functions where they're 1 to 1, and we're going to do a swaparoo, and that will give us the domain and ranges of the inverse functions. So for example, the domain of cosine inverse is the range of cosine. So our set of inputs into cosine inverse are the numbers -1 to 1. So the possible answers that you could have gotten from cosine. And its range is the domain of cosine. So the 1 to 1 part. For sine inverse of x, its range is -1 to 1. It's the possible answers you could get from sine. And its range is the 1 to 1 domain of sine. It's the possible angles you could plug into sine to get those numbers from -1 to 1. Tangent inverse, its domain is the range of tangent. So all real numbers. You can plug anything into the inverse function of tangent. So that's kind of nice. It's that it doesn't have a small domain. It's actually got a quite large domain. You could plug in any number into inverse tangent and compute the angle out. Its set of angles that it will give you are angles from -pi/2 to pi/2. So those are the angles that it can give you, the inverse tangent, not including those numbers. So you'll never find the answer be -pi/2 or pi/2 with the calculator. As an exercise, I would encourage you to just compute inverse tangent functions on your calculator, see what happens if you plug in a really big number. You should get about 1.57 as your answer, inverse tangent of 100. And if you plug in a really big negative number, say like -1,000 or something like that, you should get a number really close to -1.57. Well, those are pi/2 and -pi/2 respectively, okay? So that's what's happening there. Likewise, when you plug in a number for inverse sine, if you plug in 1, you should get pi over 2 out. If you plug in -1, you should get negative pi over 2 out. So those are kind of key things to remember, key angles. Okay, let's use the inverse function on our calculator to solve a problem. We want to find the smallest positive number x, where cosine of x is 0.7. So this isn't an easily answerable question in terms of looking at the unit circle and saying, oh, it's that angle. I know this angle from the unit circle. You know, we know what pi over 6, pi over 4, pi over 3, those kinds of angles. This one, 0.7 as an x coordinate is not one of our nice ones. It's not one of our nice x coordinates. So to find this, we're going to have to use a calculator. But first, I want you to sketch the unit circle so that we get a sense of what the answer should be. Now, here's our unit circle. Remember that the cosine inverse is from 0 to pi. So cosine inverse is actually only going to give you answers that are up here. So cosine inverse is only going to get you answers that are in the upper half plane, angles from 0 to pi. And it turns out that's actually what we want for this, because we're looking for the smallest positive x, where cosine of that angle is 0.7. And so that first x is going to be between 0 and pi. So this is actually a great candidate for just using the inverse function and finding the answer. But let's go ahead and draw what we are interested in. We need to find the points where the x coordinate is 0.7. So that's roughly here. So this would be an x coordinate of 0.7. And you could find the y, but who cares for now. So this would also be an x coordinate of 0.7. So I'm going to draw the two possible angles. And they're symmetric, meaning that these angles are the same right here. Boom, that angle and that angle are the same. But since we're interested in the smallest positive one, we're going to take just the top one. So this is the one we're going for. That's the one we want. And so we'll go ahead and use a calculator now to compute this. We take the cos inverse of 0.7. I want to also let you know that there's another way to say this. Cos inverse is how we write it, with the -1 symbol. And it doesn't mean 1 over cosine. It means the inverse function. 1 over cosine we already know is secant. It's got its own name. Another way people say this is arc cosine, ARC, cos of 0.7. So that's another way to say the angle where you take the cosine and you get 0.7. Another way to say cosine inverse. And when you're using, say, Google Calculator, you actually want to type it out as arc cosine. So I'll just show you how you can do this real quickly, so you can see that same answer. I get 0.795. So going to Google, whoops, opening a new tab, I'm going to just type arc. Here, let me move my face out of the way. Arc cos of 0.7. And typing that into the search bar in Google Chrome gives us 0.795 rad. So that's the angle. You take the cosine and you get 0.7. Let's go ahead and test it out to show that's true. I'm going to take the cosine of 0.79539. Well, I'll just use 4. And we should get an answer that's roughly 0.7, and you see it's about 0.69999, so it's going to be closer to 0.7 the more digits we add. Okay, so that is, here we go. That's how you can use the Google Calculator. You have to use arc cos, not cos to the -1. Okay, verifying our answer matches to the quadrant. So this is the last thing we want to make sure is, does this answer make sense? 0.795. Is it the smallest x? Is it between 0 and pi over 2? And the answer is yes. We already knew that this was the angle we were interested in, because that's the first angle you would get to where the cosine was 0.7. And it's between 0 and pi over 2. which is 1.57. This is 0. 1.57 is pi over 2. So in fact is the smallest positive angle where the cosine is 0.7. You could also graph the function out and see if it is the first answer. Okay, so that's a relatively straightforward one. We just take the calculator's word for it in this example, or rather the calculator's answer is the first answer, is the correct answer. This example, we're going to see the limitation of the calculator, and it's not going to give us the correct answer in this case. So we have to do more thinking. Find the smallest positive number x where the sign of x is negative 0.2. Again, starting with the unit circle, so we have an estimate or an idea of where the answer would be. We're going to sketch the unit circle out. So here's our unit circle. We need the sign to be negative 0.2. So that's the y value is negative 0.2. So that's occurring about here and about here. So we have got two possible angles. Let's use a different color. We'll use red, this angle, and this angle. Since we're interested in the smallest positive number, smallest positive x, we actually want this answer right here. So this is the x of interest. That's labeling it out. That is the x where the sign is negative 0.2. So it's in quadrant 3. So it's important to remember that our answer is going to be greater than pi and smaller than 3 pi over 2. Okay, so it's going to be somewhere between pi and 3 pi over 2. Okay, next we'll use a calculator. Sine inverse of negative 0.2 is the angle between negative pi over 2 and pi over 2, where the sine is negative 0.2. So that negative angle, that negative 0.201, that's referring to, I'm going to label this, that's referring to this angle right here. That's negative 0.201 radians, okay? And so we can see that this answer is not the correct answer. For one, it's not positive. It's not the smallest positive number, and it's not even talking about the right angle. We can't just add 2 pi to this answer to get the right answer, because there's an angle that's before that in quadrant 3, where the answer is negative 0.2, where the sign is negative 0.2. So how can we use this piece of information to actually find the right answer? Well, maybe you see it. Maybe you can look at this picture and see what we need to do. That this angle right here is congruent to this angle, that they're the same measure. And it looks like all I need to find this other angle here is to take my negative 0.2 and make it a positive number and add pi to that. So we actually can easily get this by doing pi minus that calculator's answer, 0.201. So if we subtract negative, the answer, negative 0.201 from pi, that gives us the other answer over there. That's the supplement to this one. And that's the one we in fact want. This answer is in quadrant 4. However, we know from the drawing the answer is in quadrant 3, that the actual angle we want is in quadrant 3. So the answer has to be pi minus the supplement. It's the supplementary angle. Pi minus negative 0.201, which is about 3.343. And this, we remember, is this right here is bigger than pi, which is 3.14, and smaller than 3 pi over 2, which, oh, I don't know 3 pi over 2 off the top of my head. Let's just compute that. 3 times pi over 2, 4.712. So I don't know that one so well, but it's 4.712. Okay, so it's between those two angles, and that's the one that we want. To test our answer, we'll just take the sine of this number and see if we get roughly. So we're going to compute the sine of, oops, what was it? Sine of 3.343. See that is in fact equal to, what were we trying to show? So, oh, negative 0.2. So this should be about negative 0.2. And boom, there we go. So, and again, we would get closer and closer to negative 0.2 the more digits we added on here. So remember, we had to draw the unit circle to come up with the correct answer. 3.343 is the smallest positive x where the sign is negative 0.2. So it's not just plug and chug with your calculator. There's quite a bit more thinking that has to go into it. Okay, we're going to do one more example and then call it. This last example is based off of a triangle problem. So we want to determine the vertex angle of an isosceles triangle with side lengths 4, 4, and 7. So let's go ahead and draw this problem out. The 3 steps that are a good steps to go by when doing something like this is that you want to draw it, label what you are interested in and what you know, and then maybe list out formulas that might be useful. In this case, we're going to be finding an angle, so it's probably going to be useful to list out some the SOHCAHTOA, sine, cosine, and tangent if you don't have those memorized yet. Okay, so let's draw the problem first. So we've got a isosceles triangle. This side is 4, this side is 4, and this side is 7. So boom, draw the problem. We've started labeling. We want the vertex angle, which is this angle up here, x. That's the angle we're interested in. And what we know, okay, we know those sides are 4, 4, and 7. We're going to list out some formulas that might be useful. Well, to solve this problem, we actually have to kind of get some right triangles going for now. Later on down the line, we'll be able to solve this problem when the triangle's not even isosceles for any kind of triangle. But for now, we need to get some right triangles built out of this picture. So I'm going to draw in a right triangle, right, and that cuts this side over here in half, so that's 3. So it looks like a useful formula might be sine of x over 2, half of x, because this angle right here is x over 2. I'm going to label it in a different color. Over 2, sine of x over 2 is equal to 3.5 over 4. So that opposite side, boom, opposite over the hypotenuse 4. So hey, there's a great formula. We've got we don't have x exactly, we have half of x, but we should be able to find x from this. So using that fact, we'll take the inverse sine of both sides. So we take the inverse sine of this, and that gets us x over 2 equals inverse sine of 3.5 over 4. And when we compute the inverse sine of 3.5 over 4, we get a roughly 1.065 as our answer, 1.065 radians. And so that says x over 2 is about 1.05. And so we multiply both sides by 2 to find x. And that gets us about 2.131. And if you switch that into degrees, remember to get to degrees, you just multiply it by 180 over pi. So if we wanted to take 2.131 times by 180 over pi, that turns it into degrees. That gets you about 122 degrees if you did that multiplication. But since it didn't specify degrees or radians, we can answer in either form and be fine. That's how we could solve some kind of problem involving the inverse function. Note that in this example, since all the things were positive, our angle calculation ended up being a positive angle. We didn't have to worry about the trickiness of inverse sine or inverse cosine. But when you're answering those questions like, okay, what's the first positive angle where the sine is negative, you might need to draw the unit circle, and I would always do that because there ends up being these pairs of answers that come out, and you have to be able to decide which is the right one. Okay, so that concludes this lesson. The next time we're going to look at the graphs of these functions, and then we'll wrap up this unit with sinusoidal modeling and how do you use the inverse function to come up with all the possible answers not just the one from negative pi over 2 to pi over 2, or 0 to pi if it's cosine. Okay, so without further ado, I'll see you guys next time.